So, hello everyone to a new session for the Engineer Digital Twin Talk. Today, our speaker is Jacqueline Le Moigne. We also have two more sessions for this series. On the 12th of May, we have Bentley Oaks, and on the 2nd of June, we have Alvin Hoffman. So, thank you for joining us today, and please, you are welcome to join the next sessions as well. Our today's speaker is, as I mentioned earlier, Jacqueline Le Moigne. She is the manager of the Intelligent System Technology Group, a part of the Earth Science Technology Office from NASA. She has over 180 publications, including more than 30 journal papers and book chapters. She has received the NASA Exceptional Service Medal as well as the Goddard Information Science and Technology Award, both in 2012. Her research areas include image registration, AI, autonomous systems, Earth system digital twins, as well as high performance and onboard computing. Today, she will introduce the Earth system digital twin concept, as well as its benefits to Earth science, a few use case examples, and the technology challenges associated with building Earth system digital twins. Thank you very much for willing to present us. The floor is yours, Jacqueline.
Okay, thank you very much for this introduction and for inviting me today. So yes, so as Leonard just mentioned, I am going to talk about NASA Earth System Digital Twin, which is an initiative that we started about 4 years ago in the Earth Science Technology Office. So first of all, I just wanted to position where the Earth Science Technology Office is at NASA. So, if there are several directorates at NASA. We are part of the Science Mission Directorate. As part of the Science Mission Directorate, the Earth Science Technology Office is in the Earth Science Division, and the role of the Earth Science Technology Office, or ESTO, is to look at technology, hardware, and software that will be needed by Earth Science in the 5 to 10 years framework. As part of so technology really is one of the elements out of 5 elements in the Earth Science division, and really interacts with these other elements, both to infuse the technologies that are being developed within ESTO, but also to take requirements and science wishes from the other elements and develop the technologies that will be needed by Earth Science. So within ESTO, the IST group, or Intelligent Systems Technology Group, that I am managing, is looking at investigating and funding technologies in information and intelligence system and software, as well as new computer science technologies that will be able to respond to these needs of Earth science within that time frame. To reach this vision, the objectives of IST are to develop technologies both from an observation as well as an analytics point of view that will optimize Earth science mission returns. So the idea is to develop technologies, for example, in new observation capabilities such as distributed sensing, but also in analytics using the flexible information integration, agile science investigation with advanced algorithmics and analytics, but also developing these integrated Earth science frameworks such as digital twins, which will include interconnected models, ingesting timely and relevant observation, and integrating AI and ML tool to support this near and long-term policy and science decisions by delivering actionable science and information. So within the IST group, we have 2 programs. The Advanced Information Systems Technology, or AIST program, that looks more at the observation side, so looking at this this new observation concept that combine various distributed and coordinated observing assets that can be in space, in the air, or in situ. In the AIST program, we are also looking at advanced computational capabilities such as quantum and neuromorphic computing. But we are also looking at technologies that are probably at a lower maturity level. For example, machine learning, which have a cross-cutting interest in earth science, but also techniques that looks at early concepts for observation and computing. The second program is the Advanced Modeling program, Advanced Modeling Technology program that I am also managing. And this is a program that includes the Earth system digital twins. So all the technologies that are needed for developing this digital twin, as well as some early and more advanced prototypes, but also looking at advanced modeling capabilities such as surrogate model emulators, but also improving the model performance, the classical model performance using advanced mathematics or advanced computational capabilities. And also looking at ingesting state-of-the-art mathematical techniques into these models and the digital twins. So, for example, not only in terms of machine learning, but also in terms of uncertainty quantification and provenance. And causality also is something very important. So, now, what do we call a system digital twin? So this is really going into the topic of this talk. So we at in ESTO we have worked a lot to come up to these definitions that really integrates the definition, many different definitions, but really is responsive to what we need, why we need digital twins in earth science. So we consider earth system digital twins as information systems for understanding, forecasting, and conjecturing the complex interconnections between among Earth systems, including anthropomorphic forcing and impacts to humanity. So it goes really in both directions. And really this covers this idea that at the core of a digital twin, there are three main components. The first component that we call the what now is really the digital replica. And the digital replica is an integrated picture of the past and current state of the Earth system, or it is a snapshot at some point of the Earth system. The second component is what we call the what next, and these are all the forecasting capabilities, which means that based on the digital replica and based on nominal condition, what is going to be the state of the system in the future. And the third core component is what we call the what if, or the impact assessment, and it's the capabilities of being able to run different what if scenarios, which means that using the digital replica and the forecasting capabilities, can we look at what would be the state of the Earth system under different conditions. These are initial conditions or boundary conditions, and being able to run this what if scenario very fast so that we can run many different scenarios. So we will see later, but this is so really the Earth system digital twin is a framework that goes around these three main components, and that will provide capabilities for these three components, using of course machine learning at every stage of the process, but also being able to interconnect models, so interconnect Earth system models, but also interconnect these Earth system models with human model and infrastructure models, for example, health or infrastructure of a town, and being able also to ingest in real time, near real time, or timely, depending on the Earth system that we are looking at, we being able to integrate this continuous observation, so that the digital replica is a real digital twin, and is not is synced with Earth system process. So why do we want to look at digital twins in Earth science now? So I feel like we are really at the confluence of three main phenomena. We have now been able to collect Earth data continuously for more than 50 years. So we have a wealth of data, not only at NASA, but ESA, all the space agencies in the world. But now we have also data from commercial from commercial entities, from even from universities. So we have a wealth of data that we can utilize. The second event is that there has been, in the last few years, there has been really fast and tremendous advances in computational and visualization capabilities. So it is now possible to be able to take all of this data and utilize them fully. So this is it's what brings the capabilities to these digital twins. And finally, the third thing is that because of climate change, the information that is produced by all of this data traditionally was of interest to Earth scientists and to some decision maker, but now there is a really great demand for this information, and this information is becoming of interest to many new non-traditional users. So it can be for the farmers, for the fishermen, for the ordinary citizens, as well as for urban cities from different sizes. So there is a really very large, wide range of users that will need this information. So we need really to create this information system that will be able to respond to all of these demands. And now we have the means to create these information systems. So when we started looking at Earth system digital twins, the first thing that we did, because we are at NASA and we are a science organization, we first looked at the benefits to Earth science. And if we look at all the different domains of Earth science, we could find benefits, and I am not going to go through all of them, but you can see the main bullets, and you can see that they are really, we can really identify benefits of a system digital twin to many different areas of Earth science. So based on these different benefits, we looked at different use cases that I will introduce in my next slide. But before that, the other question that we ask is what is different between this new Earth system digital twins and what has been done since 40 years or so in Earth system models? And is digital twin just a new buzzword for modeling, or is there something different? So I feel that there are four main differences between digital twins and Earth system models. The first one is this continuous integration of timely data. So I like to use the word timely because in some cases, for example, for a hurricane, we will need real-time data. But for other Earth systems like glacier melting, we will need only timely data. So it's really data that is relevant. The time frame is relevant to the system. The second difference is this interactivity with the users, being able to provide this capability of playing with the models or playing with the data. And also for policy decision making and for conjecturing or planning different scenarios. Of course, the access to the digital twin by different users is not going to be the same, and not anyone can play with the models at a very deep level. these information systems, these digital twins, will need to have different level of access, especially from a model point of view. The third difference is this integration of anthropomorphic forcing and impact models with Earth system models. And this has been done in some Earth system models to a certain extent, but it is not systematic. So there the idea is to be able to create capabilities to interconnect these models in a relatively easy fashion. And this interconnection can be a tight coupling, or it can be a loose coupling, which means that the information from one model can feed into another model, or we can create machine learning models that really couple multiple models together more tightly. And finally, the last difference is this heavy use of machine learning at every step of the digital twin. So in terms of data fusion, data assimilation, but also for super resolution and downscaling, for speeding up the models. And when speeding up the models, we can not only run a larger number of hypothetical scenarios, but we can also increase the spatial and the temporal resolution. And finally, machine learning can also be used for causal reasoning. It's still a domain in which there is a lot of research that is being done and that is not fully developed. But this will be very important for the last stage, this impact assessment stage of the digital twin. So the digital twin also relate at NASA to this new strategy that is called the Earth Science to Action strategy. And the idea here is to be able to provide this actionable information. So really take the results of the science that is being done at NASA and use it for this actionable information, and to be able to help the many types of users and decision makers. And the two main objectives of this Earth Science to Action strategies are first to holistically observe, monitor, and understand the Earth system, and the second one to deliver this trusted information for Earth resilience activities. So digital twins really respond fully to these two objectives, and so this is why it is important to relate digital twin to this strategy. So from a technology point of view, which is really the goal of our IST group and the two programs, especially the Advanced Modeling Technology Group program, we look at this Earth system digital twin as really a continuation of what has been done by our program since about 10 years or so. So we developed these novel observing strategies that allow to observe, target, and coordinate, especially using distributed assets. We also developed these analytic capabilities. We had something called ACF, which is Analytic Collaborative Framework. So we developed multiple frameworks for facilitating this science investigation, integrating computational and analytics capabilities. So if we add to these two capabilities, so with NOS we can have this timely integration of data. With SCF analytic capabilities, we can have all these analytic capabilities that will be able to compute the digital replica, but also integrate this modeling for forecasting more easily. So if we integrate these capabilities with the digital twin infrastructure, more advanced even machine learning and modeling, and we add these capabilities of interrogating, simulating, visualizing, intervening, and assessing, we get this digital twins. So this is really building on the technologies that have been developed in the past 10 years, but adding this framework around it to build these digital twins. So in in IST, in terms of digital twin, we have all of these different projects, and I am not going to read all of these titles, but these are all the different projects we have altogether in IST. We have about 62 projects, and we have around 25 to 30 projects that are related to digital twins. And we can categorize these digital twin projects in terms of three different classes. The one that are looking at infrastructure capabilities, so in terms of, for example, model coupling or reproducible containers is something also very important. Then we have all the projects that are related to developing new machine learning-based surrogate models and emulators in different domains. So for atmospheric composition, for weather forecasting, we have an interesting project about climate tipping points simulator. And then finally, the third category is dealing with prototypes. So we have different prototypes. So some of them are smaller prototypes that are focusing on one of the three core capabilities: the what now, what next, what if. But we have a larger project, which is the one at the very bottom here, the coastal zone digital twin, that is really looking at the entire approach end-to-end and developing a framework that will be reusable for other digital twins. So in terms of machine learning, I'm not going to insist a lot on this slide, but really we can see that machine learning is very important for advanced modeling at all steps of this very simplified Earth system modeling pipeline. From the onboard autonomy to access this data and process them very quickly on board, so that they can be delivered to the system more quickly. But also, of course, machine learning to help the physics-informed machine learning models, to create full machine learning-based surrogate models, but also to accelerate the simulation, to plan for science-driven observation. So at every step of the Earth science modeling process, machine learning can be used. And in particular, we have been the machine learning techniques that is currently that is the most recent and that is the most promising, probably, is foundation models. So we have a few projects looking at foundation models for different things. For example, we have one for learning changes in images, in remote sensing images. Of course, for physics-guided learning, but we also have a project that is looking at digital twins for and large language models for visualization and for user interfaces, really. So this will be also something that could be very interesting for digital twins, to provide intelligent user interfaces that could help users that are not necessarily familiar with Earth science models, and will be able to interpret their queries. So in terms of prototypes, as I said, we have different prototypes that are being built, and these are a few examples of these prototypes. We have one for agriculture applications that is particularly looking at what if scenarios. So looking at, depending on different projections for the future, which kind of crop would work better, under which conditions, at which locations these crops would work the best, and when to plant it, and how to take care of it. the predicting what we breathe is an air quality and transportation digital twin, which is looking at the relation between different modes of transportations and the air quality in a large city like Los Angeles. So it's building on air quality models, but also they have a lot of information in terms of transportation, what are the roads with the largest traffic, but also they also have access to health information and, for example, for asthma attacks. So they can relate all these different models to each other and interconnect them. We have also a project that has been done collaboratively between NASA, JPL, and CNES, looking at flood prediction and monitoring. And there, a digital twin has been developed on both sides, and so they have been able to look at challenges related to the federation of these two digital twins. We have a model looking at the coastal zone. So this was a preliminary project towards our larger coastal zone digital twin project. And this was also, again, to relate health of vulnerable population in the coastal zone to the issue of floods and extreme weather in the coastal zone. And the last one here is called Terra Hydro, and looking at hydrometeorology digital twin, and particularly looking at developing a machine learning a tensor-based toolbox that will enable to couple multiple models using machine learning. And so all of these prototypes are very important to look at what are the different ways to build a digital twin, and in particular to identify what are the basic building blocks for building a digital twins, and also to answer all these overarching questions about how to build and operate digital twins. So how can we interoperate and federate this digital twin? Because we can imagine that in the future there will be a network of digital twins that are going to be built by different organizations, different countries, and that are going to look at different Earth systems, or that are going to be more local or regional or global. So how do we take all of these digital twins, and how can we federate them so that they can interoperate and be compatible? So we will need to define some standards, some protocols, some interfaces, but also how do we ingest this timely data into this digital twin? Which kind of computational resources are going to be used? And the important thing is, how are we going to validate these digital twins? Because if we look at AI/ML, there was a challenge of trust in this system, and there is still a challenge of trust in AI and ML systems, and there will be the same type of challenge for digital twins. So we need to validate and bring the trust in these systems to the user. So this can be done by making sure that we have a certain level of fidelity, that we can quantify the uncertainty at every step of the chain. And finally, the last question to answer is how are we going to sustain this digital twin in the future, and how are we going to address software configuration changes and security and full life cycle management? So these are all kinds of questions. So at the same time, we also have been defining a digital twin architecture framework that is not a prescriptive architecture, but tries to define a framework so that it will facilitate this interface between multiple digital twins. So we look at this architecture framework by relating it to the definition that we adopted for digital twins, with a digital replica being one of the elements of this architecture, the nominal forecasting system being another one, and the impact assessment subsystem being the third one. And with all these three elements surrounded by the framework, by the ingest of the data, by the control, of course, of all of the system, and by this user interface. But we also add the digital twin records, which is probably the equivalent of it can be a data lake or other types of record, where we can keep the information that is important to this particular digital twin. So mainly the framework looks at what are the main architecture principles that are important for building this digital twin. Modularity is probably the top component, that the top principle that is important, because it will allow us to evolve this system more easily than if they are kind of a black box where all the components are integrated too tightly. So we are trying really to have a very modular system. We need to also design them as reusable system if possible. And of course, with open source and open science principle, so that different components can be used by different organizations, and with this open standard interfaces for federation, and of course, the idea also is to define this ESDT architecture with user interfaces that, as I said before, can respond to the need of multiple types of user, what we call from farmer to scientist. And yes, and as I said below, so we are really trying to reuse these components beyond a single architecture, and our role in the IST program are really to define the technology gaps that exist, and try to develop these new technologies. In some cases, the technology exists and needs to be adapted to the digital twin. In some cases, it doesn't exist at all. For example, interconnected models, it's still something that is very early. So in some cases, we need to develop these technologies. So a particular example, as I said, that we have been looking at, and this is in collaboration with CNES, that works under the Space Climate Observatory, and with NOAA also. And there, our what we call the grand vision is to develop an Earth system digital twin for coastal zone, to understand the changes in coast, but not only in coastal flood severity, but also in land and marine morphology, in nutrients and water quality, in ecological makeup to relate it to the sea level change, and of course to look at the short-term and long-term risk to extreme events adaptation, and of course for sustainable development, disaster management, tourism, quality of life, and so on. So this is really our grand vision, and of course we are going to go in steps, but this is eventually what we want to achieve. And in blue all around here, you can see all the different questions that a user could ask from this digital twin. So the questions are can be from a urban decision maker, as well as from a scientist. So For these coastal zone digital twins, we have been looking at, so our first steps is to look at these different regions of interest. So build them probably more local to start with, but then after that, extend them to a global digital twin. So we have been looking at 3 regions of interest sites from the US side. So from the US side, we are looking, the first regions of interest we are looking at is the Chesapeake Bay. But then we would like to look at the northern coast of the Gulf of Mexico and then to Alaska, which presents other challenges in terms of Earth systems. And on the French side, we have been looking at also 3 different sites. Of course, the coastlines of France, but also at Nokwe in Benin, with a lake that provides interesting challenges. And of course at New Caledonia, which is an island and which has topography, bathymetry, and land use challenges. So this is here it's a scope from a US point of view. So as I said, our first region of interest is the Chesapeake Bay, and so for the Chesapeake Bay, we have been looking at 2 different use cases. So if I summarize this effort from the US side, the objective here is to define these prototypes that will demonstrate, of course, the potential of Earth digital twin to Earth science, but also that is, as I said before, that is modular, scalable, and that can be easily modified. And has the potential to be federated with other digital twins. And as I said, also to identify the technology gaps. So from a high level requirement, we assume the digital replica to be computed continuously. So we have not yet decided about the refresh rate, but it will be probably a minimum of 6 hours to 1 day, and maybe a minimum smaller than 6 hours. But it will not be computed on demand. So there will be a minimum digital replica with a minimum amount of essential variables that will be computed for the digital replica continuously. And then if other information or data is needed, it can be asked on demand by the user, but there will be a minimum digital replica computed continuously. Then for the what next, it will be computed either continuously, but probably with a slower refresh than the digital replica, or it can be also computed on demand when there are extreme events, so for forecasting capabilities. And the what if will always be on demand because this is really user dependent, so it depends on the questions of the user. So depending on the questions of the user, the information produced by the what if, the impact assessment module will be responding to these questions. From a supporting infrastructure, we are using a cloud environment in Amazon that we have running here at NASA. And we are using GitLab and RabbitMQ for a centralized message broker. And we are also using standard interfaces based on what is already available from OGC. And if new standards are needed, we will define them, and we will work with the international community to define them. So as I said, we are looking at 2 use cases, one in urban flooding, and the other one is in harmful algae bloom. So for each of the use case, we are defining what we call personas. So these are our different types of users, and so we define these personas to anticipate the type of information and the type of questions that each of these users and the type of interfaces that each of these users will need. So for the flooding use case, we have an emergency manager, a flood forecaster, an urban planner, what we call tribal council that looks at kind of midterm to long-term effects of the floods. and of course Earth scientists, which will look at it more globally and in a much longer time period, over 10 to 40 years time period. So, and for the water quality, again, we have for different types of users or personas. Again, from the shellfish aquaculture farmer, that will need some weekly to monthly forecast of anomalies to make sure that the water quality is appropriate for their aquaculture. To tribal council, again, for looking for planning purposes, for water quality and habitat conditions, the public health official, and finally the earth scientist, again, looking at a longer time period, but also looking at communicating science. So it goes really in both directions again. So for the architecture, we decided to use a publish subscribe type architecture with a message bus based on RabbitMQ, and all the different modules, the different components of the architecture are communicating with this message bus when new information is ready, and of course this information will be ready in the cloud. And we have a control monitoring subsystem that is right here, that has all these different capability to coordinate between the different subsystem, to provide automated resource optimization in the cloud, to collect and display the status from the different system, to check for system malfunction, and to provide users with information regarding resource availability, for example. So these are all the input and output of the control and the monitoring subsystem that gets the status messages, the subsystem data, and the operator and user request, and provide these different outputs in terms of control, display pages, and alerts and notification. For the digital replica, what we are doing right now, based on the use cases, so we refine the use cases, and based on the use cases, we define some essential variables that are going to be used to build this digital replica. That will probably be a data cube. There is still some discussion there. But the information subsystem that includes the digital replica, the ingest subsystem, and the data digital twin record will need to deal with this asynchronous and continuous ingest of observational data, also the ingest of model outputs as needed, and the processing of all this ingest to put into the digital replica, and notifying the other subsystems through the message bus when new information and the new digital replica is available. From a nominal forecasting subsystem, so this is a preliminary thoughts about the forecasting subsystem for the flood models, where there will be a forecast model that will be developed using an emulator, and maybe in the future also using a foundation model. So there is just a CNN, but and autoregressive ML. But in the future, we are also planning for a foundation models, and that will again communicate through the message bus and to the CMSS. For the impact assessment subsystem, so the idea here is to investigate the impact of the condition of the phenomena, and also related to other phenomena and to a human impact and forcings, and to initialize this analysis based on the current state of the DR and on the future state of the forecasting subsystem. So. And again, they are going to use AI models to do this impact assessment. So if we come back to the Earth Science to Action strategy, So we have defined these different use cases. So coastal zone is at the bottom. There is one of them, but we are also looking at different other use case and other prototypes. And these prototypes, as I said, are going to inform the digital twins that are going to be built for this Earth Action to Earth Science to Action focus areas. So there are about 15 areas that have been identified, and so this will be really an agile iterating process between this development of prototypes and the development of the operational digital twin that will run for the Earth Science to Action strategy. So overall, this is our roadmap looking at first a coastal zone prototype. We are going to have a demonstration in 1 year. In February of 26, we are going to have the first demonstration. And then based on this coastal zone demonstration and first prototype, on other prototypes that we are developing. And of course, we are also collaborating with international organizations. So we hope to advance our architecture based on what we learn and also from our collaborations. And eventually, the idea is to build this operational digital twin that will respond to the needs of the Earth Science to Action. And these are the, I think it's my last slide, looking at the question challenges. And I already talked about most of them. The questions that remain are really how are we going to do this ingestion of data, not only in terms of data that are already collected and that we need to access very quickly from archives and data system, but how are we going to integrate also this continuous data, the computational challenges, how much computational capabilities are we going to need? Right now we are, of course, running in the cloud, but some of our models are going to run on HPC. Some of them are going to use GPUs, but in the future, are we going to need quantum computing, neuromorphic computing, and of course, adding edge computing in situ and on board? So we did some basic computations, but some computations have been estimated also. For example, for destination Earth, when for a global digital twin, it was estimated that operating a digital twin at full scale would require about 20,000 GPUs. So can we afford it, or can we decrease these requirements? Of course, all the federation challenges that I already talked about. One interesting development that is an NSF initiative that is looking at an open knowledge network that could be the kind of an overarching capability that would provide this organization of information coming out of all these digital twins. So it could create, so all the output of all these different digital twins could be integrated in this open knowledge network. And then the digital twin could also go to this network to get information that they need. So this is an interesting development that is still an early maturity level, but that needs to be followed. The visualization challenges, different users will need different types of visualization. So it's a lot of information. How do we visualize it in an optimal fashion? The trust in digital twin, as I already talked about, with validation, uncertainty quantification, provenance needs to be looked at. And finally, which sustainable digital twin governance model need to be adopted. And there we can look at different level from a technical point of view to a policy to an economic point of view. So these are different challenges that will need to be looked at in the future. And you can go to these different websites. We conducted a workshop in 2022, and there is a report available online. There is also all of our use cases are available online. We also conducted a small workshop for standards for interoperable digital twins in 23, and our architecture framework document is also available online. And if you want to look at all of our projects, you can also look at our ESTO portfolio webpage. All the projects are also on the summary, and the quad charts of all the projects are also online. And I think that's it.
Thank you very much for your very interesting presentation. Now it's time for the Q&A session. So Martin, can you please stop the recording?
Yes.